Okay, one of the last topics of this function of two variables, maxima and minima. We are back to the lectures, right? And we have 45 minutes, and we hope we will cover this topic. In simple words, maximum and minimum values of function are the values. So first, the maximum values of the functions of such values. The value are such values where function, in certain domain where function cannot have greater values than those values. So those values are called maximum values of the function. And similarly, minimum values of functions are the least values of the function when compared to the other values. So there will be no value let's say less than that value. So that is called least value. So in graphical in geometrical representation, if you look at this function, so this is the smallest value, and this is the minimum value, and this is the maximum value. In graph, the maximum value attained by function, and so this is in a simple words, or in a, let's say, naive words. Now particularly if you look at this example, it's a graph of f of x comma y, some function which represents hills and valleys. So these are valleys, let's say these are hills, the tops. So it's apparent to say that this peak shows the maximum or the highest value of the function, and this peak lowest or minimum value of the function. So these are roughly called the maximum and minimum value of the function. But mathematically they are explained as well. There is a difference between so the maximum values are classified into two, let's say, categories. One is local maximum, and other is absolute maximum. The same case is with minimum values. So there are local minimum and absolute minimum. Local minimum is the value in certain local domain, and absolute maximum is the maximum value in the complete domain. So there are 2 points a comma b where f has a local maximum. That is, f of ab is larger than nearby values of this. It means now this point can be considered or can be thought as a local maximum, because if you only consider values nearby this point, let's say this region, so this is the maximum value. But if you extend your domain to this one, then this is your absolute maximum. Or if you consider this domain, then this is absolute, this is local maximum in this short domain. But in a larger domain, so this is absolute maximum. So local maximum is when you consider very local domain, small domain, right? And when you have more than one local maximum, so the maximum of all these local maximum is basically absolute maximum. That is a relative concept. Same is the concept with minimum, right? So I already explained in terms of maximum. This is local minimum. This is also local minimum, but the least of these two is absolute minimum, which is this one. Okay, so this is explanation. Now the formal mathematical definition about local maximum and local maximum value. So first, local maximum. Local maximum are the values of independent variables for which function attains least value in certain domain. So a function of two variables formally has a local minimum at this point a comma b, the values of x and y, if f of x comma y is less than this value. Now this value should be greater than for all other values of x and y, right? So function attains maximum value if and only if we give input of x and y as a and b, and if we give any other input, the function must attain or have small value, the least value, and x and y should be near A and B. This indicates that you have to take in small domain, small, let's say, part of the domain. So this will be indicating your local maximum. Okay? Now this point AB is local maximum, and this means f of A is when this is less than this number for all points in this, then this value f of A comma B is called local maximum. Now there is a difference. So this is local maximum value, and A comma B is local maximum. All right. There is a different local maximum and local maximum value. Local maximum value is the value of function at local maximum point. Symmetrical definition or similar definition for minimum is A comma B is a minimum point when function has minimum value. Then all other points near or in the neighborhood of this A comma B. So theoretically we will write f of x comma y is greater than this one. This is the smallest value. When x and y are in surrounding of this one or in neighborhood of this one, then f has a local minimum is at this point. So this point is local minimum. This is local minimum of f, and this is local minimum value at that point. So this is formal definition. Now absolute definition of absolute minimum and maximum. If inequalities in definition 1 previous for definition for maximum and minimum hold for all points in the domain, not only in the neighborhood or certain small domain, but in complete domain, then that will be absolute maximum or minimum, right? And that particular point. Okay, now there is a theorem which basically defines or gives criteria to find minimum and maximum of a function of two variables. Okay, so the theorem is named as theorem 2, and if f has a local maximum and minimum at this r, so any of this are at this point, and the first order partial derivative exists, then right. So if you test or if you check their first derivative is 0, then this point will either be minimum or maximum. Right. Now this is because if you remember, you have discussed definition of derivative, partial derivative, basically with respect to x. So this is rate of change of slope in x direction, and this is rate of change of slope or rate of change of slope of tangent in y direction, right? So when there is no change in y direction, it means that point is critical point, and that is the maximum. The function is not changing in certain direction y, so that change is 0 over there. The tangent is basically rate of change in y direction. So I'm rewriting this. This is not correct. Rate of change in y direction or slope of tangent in y direction. It means that slope is parallel to x-axis on that point, or even in the minimum point. The minimum point slope is tangent with the y-axis or in x-axis similarly. So this is very similar concept, the calculus one, where we used to talk about the first order, first one variable function, and there when the derivative was 0, so that point was supposed to be critical point, maybe maximum or maybe minimum. So in two variable we have point a and b, and if both variables both partial derivatives are 0, then that point can be critical point, say maximum or minimum point. Okay, so this only highlights the the point under discussion is either minimum or maximum. There is another test or another criteria to, let's say, know about if the point is maximum or minimum. All right, so this is proof. I am skipping this. I don't think it is that important for you. And geometrical interpretation, I already explained. If f of x comma f of x is 0, or the first derivative, partial derivative with respect to x is 0, it means that slope of the tangent is 0 in direction of x, and f of y is 0, the slope of tangent. So this is the same thing. The graph of f has a tangent plane at a local maximum or minimum. So that point, if it is maximum or minimum, the plane will be horizontal, right? Now, collection of there is another definition basically. So collection of, you can think about this or take it as a definition. A point is called critical point or a stationary point. Stationary because that is the stagnant, or the point where the tangent of the slope is not moving basically, or it is, I mean, in a standing position. It's parallel to the axis. So that will be critical point if both are these 0, and point can be maximum or minimum, both points can be critical points. So critical means maximum or minimum. Okay, there is another case. The point is supposed to be critical point if any of the one derivative doesn't exist. It means the tangent in one direction is okay, parallel to x-axis, but tangent in y direction does not exist, so it's infinite or like this. So in that case also, that point is also called critical point. But that point can be taken as a local maxima or minima. Okay, so theorem 2, in other words, it says that if function has a local maxima or minima, then that point will be critical point. Okay, and so this second condition, one of these derivatives, partial derivative, does not exist. So this indicates that not all critical points are maximum or minimum. We have also settled with this idea in calculus 1, that not all critical points are maximum or minimum. So at a critical point, function could have local minima or local maxima or neither. So remember this one also, right? So let me amend this one. Neither, because of this condition. Because of this condition, right? The second condition. Okay, and save it. Okay, so now coming back to the example part, your favorite part perhaps. Okay, how we can find local minima and local maxima and after the functions. Now this is a given function, the two variable function, a quadratic polynomial function in two variables, x square plus y square minus 2x minus 6y plus 14. Now, in order to check if there is a critical point or maximum or minimum point, so find derivative with respect to x, with respect to y, 2x minus y, 2y minus 6. Now, if there is a point, critical point, these both derivatives should be equal to 0. So force them to 0 or equate them to 0 to find maxima or minima. So when you equate this is equal to 0, you get x is equal to 1 and y is equal to 3. So this is the only critical point. Now this can be minimum or maximum or neither. Okay, so continuing this example, and we have rewritten this function into this form, right, to check if it is maxima or minima. Now since this is always zero, oh sorry, always positive, this is always positive because of square root, and this is 4 greater than 0, so the function is always greater than 4, right? So if you plug in this point 1 and 3 into this one, into this function, so let me explain in a different way. So f of 1 comma 3 is 4, and f of x comma y is greater than or equal to f of 1 comma 3, which is equal to 4. Now function is always greater than 4 because function is equal to this one plus some amount from this plus some amount from this. Now this amount will not cause any decrease in this 4. Basically it will add something in the 4, as this is always positive because of a square root, and this is always positive. Similarly, this is always positive, and this will add something to this 4. It will not cause any decrease. So f of x comma y, when we use any values of x and y, this complete figure or number will always be greater than 4, right? Or at least it will be equal to 4 when we use x is equal to 1 and y is equal to 3. Even if you use x is equal to some negative number, let's say minus 100, so this amount still will be positive and will be added in this 4. So the result will always be greater than 4. So this number is always, and for every value of x and y, right? So if you use any values of x and y, this function is always, greater than 4. So at this point function attains or have a local minimum because function have always greater values than this 4, and this 4 is local minimum of the function, and this point is called local minima or local minimum, right? And in fact this is absolute maxima or minima because this function is a polynomial function and it is continuous function. Polynomial functions are very easy to sense or to understand. They only have a, let's say, one local minima unless they are not periodic one. So that's why this statement that it is also absolute minimum, it means there will be no other local minimum. Okay, so well, we are done till here. All right, so done with example 1. And if you want to see geometry or the figure geometry graph of this two variable function, so you will have this parabolite, right? And in this parabolite, so 1 comma 3 is the minimum point where z is basically 4. So this function is increasing like this. There is no other minimum point below this point. So this is the only minimum point, so absolute minimum, a geometrical, let's say, confirmation. And of course we cannot do this confirmation with a pen and paper. We need a software, graphing software like Desmos and GeoGebra or whatsoever. Okay, another example, find extreme values. Now this is a new term, cool. So extreme values are maximum or minimum values. That can be both values. So this is function f of x is minus 2, f of y is minus 2y, and when you equate these is equal to 0, so this is minus 2x minus 2y, and both gives you a point xy, their values as 0. So this is the only critical point which we can have, which we had from this discussion. And now let's check if it is maxima or the minima. Okay, notice that now the analysis to check if it is maxima or minima. And this is an interesting part. Okay, notice that for the points on the x-axis, we have y is equal to 0. When y is equal to 0, we move x, right? So, and the function is y square minus x square. So this complete function, when y is equal to 0, will be less than 1 unless x is not equal to 0. So if x is positive or negative, this complete amount will be negative, right? Next, for points on the y-axis, when x is equal to 0, this is always positive because it's y square, and here you force this term, second term, to be 0. Okay, and the next is, thus every disk with center contain points where f takes positive values as well as points where f takes negative values, right? So this is not a extreme point because function has smallest values and also largest values on any disk, means a two-dimensional domain. So we write in 1D or in one variable we write interval x belongs to, let's say, a comma b, or x is less than this, but in 2D we say x comma less than ab and y less than c and less than d. Okay, so this is disk, one and one. Okay, the round disk. So this is not minimum and maximum because the function attains the negative, also the positive values, and this is 0 value. So f has no extreme value at this point. So if you plot this function, you will find that, okay, maybe it's plotted here. No, illustrate the function need not to have maximum or the minimum critical value. So y square minus x square, it's a function of type, give me a minute, I will check it down. X square minus y square minus x square. Okay, so this is the same basically function. This function, the graph of this function is this. Now this is the point 0. This point is the 0. Now this is neither minimum nor maximum, because if you go along this path, you will have a more maximum points along this path, and if you come along this path, you will have more minimum values. So, and these values go to the infinite, values. So basically there is no extreme value. You can go to the plus infinity and to the minus infinity. Now, interesting point is if you, I mean, it has a horizontal tangent plane z at origin, but if you only, I mean, if you only let's say go along with this y-axis, I mean, you consider x is equal to 0, then this point is minimum point. This point is because if you go along this y-axis like in this way, right? So like this way. So for this function, this point is basically minimum. And if you go along this x-axis like this, and then this point is maximum point along x-axis, so it can be extreme maximum point only with respect or in direction of x or in direction of y, but not in both direction. So this is the conclusion, it's written here. Now this point is maximum point in x direction, is already so this is the point, this is maximum point, and this is like y, so this is minimum point in the direction of y, right? Okay, so it can happen, I mean, we can have minimum direction in one, minimum point in one direction but maximum point in the other direction. So this is same explanation, and it's the same, it is sometimes called saddle point, right? So the shape of the saddle. So to, now this is important statement, critical value and extreme values, critical point and extreme values, I mean relation. So we need to be able to determine whether or not a function has extreme value at a critical. Now this point is critical point, but because we found this point by forcing the first derivative with respect to x and with respect to y to 0, are equating derivatives to 0. So these are critical points, but we need to distinguish whether this critical point is extreme value or not. So there is a test which gives us, let's say, criteria. Now this was the vague test, and it required analysis of the function in the surrounding, whether function is increasing or decreasing or whatsoever. But this is a theorem well settled result which gives the criteria. So finding critical point is easy. You just find partial derivative, equate partial derivative to 0, and you get point. But next is how to check if it is extreme point. Extreme means minimum or maximum, or it can be neither. So this is the test, and it is called second derivative test. Very important one, remember, and it is masked is theorem 3. So suppose that second derivative exists, second partial exists, and first derivatives are 0. It means this point is critical point. And then this is theorem. Find so d is a f of x, f of y minus f of x comma y is equal to 0. Now if d is positive, this complete term is positive, and along with this d is positive, second derivative with respect to x is positive, then this point is minimum. And if this is positive and f of x second derivative is less than 0, then this is local maximum. So if this is positive, it's minimum. If this is negative, it's maximum. Second derivative is negative, then it's maximum. Second derivative is positive, it's minimum. And if this is 0, this is not greater than 0, the d, this quantity, then it's neither, the third case. So it cannot be either maxima or minima, right? So you can verify your previous two examples with this theorem. It's simple. Let me remind you again. keep this part dummy. If second derivative is positive, it's minima, and second derivative is negative, maxima. Right, and if this d is less than 0, we have no point. Okay, so in case of C, the third point, this is called saddle point. जो आपने previous example में देखी, that is critical point but not maxima or the minimum. The previous example में it was a saddle point, and graph of f crosses its tangents plane at the. Okay, so this is some geometrical information. So we have two cases, d is positive, d is negative, and if d is 0, then this is the limitation of the test. So our test doesn't give us any information, and in that case f could have a local maxima, local minima, or anything. So basically test is failed at this point. So most of the time it works, d is either positive, and most of the time it is positive unless it is the saddle point. Okay, so we have three cases. D negative, it is saddle point. D positive, then f of x positive, it's minimum, then f of x negative, it's maximum. All right, now just remember the formula of D. It is simple, f of x, f of y minus f of xy whole square, or you can write in this determinant form. So f of x, f of xy, f of yx, f of y, and this is equal to this D. Now this example, find the local maximum, minimum, and saddle points. We have to check which point function has, so it depends upon the nature of the function. So first of all, we need to find critical point. So first derivative with respect to x is x power 4, it means 4x cube. Derivative of this y term is 0, minus 4xy. Derivative of this with respect to x is minus 4y. And okay, similarly fy is this. Now we equate these equations to 0 and get the values of x and y if possible. So equating these equations to 0 and solving these equations, we will get x is equal to 0, x is equal to 1, and x is equal to minus 1. Now you will be wondering how we can solve this equation. So from this second equation, no, from this first equation, this implies y is equal to x cube. Now put it here. So if you plug in y is equal to x cube and then whole cube minus x is equal to 0, this will be x9 minus x is equal to 0, and then x8 minus 1 is equal to 0. Factorizing this will end up with these factors, and in the end we will have these three roots or values of x. And after getting these values of x, what did you assume in the start? Y is equal to x cube, right? Do you remember? Here, y is equal to x cube. Now use these values of x, you will get values of y. So 0 gives you 0, 1 gives you 1, y minus 1 gives you minus 1. So these are three critical points. Now we do not know which of these point is maximum, minimum, or saddle point. All right, so we apply second variable test, and this is second variable with respect to x, this is xy, this is yy, and this is d, or in alternative notation, this d is equal to f of xy, f of yx, f of y, and you sort out, you will get this one. Okay. Now, if you notice, this is always greater than 0. Whatsoever values of x and y we choose, this will be always positive. No, not for, I mean, this 0 point at least. So if you plug in 0 it will be negative. Now at this point 0 d is negative, so this is saddle point, right? So, done about the first point. If you plug in 1, so your d is positive, and once your d is positive, you will check f of x at 1 1, and this is also positive. This means this point 1 1 will be minimum. All right. Similarly, when you plug in this point and d, you will notice that d is positive, and next you have to check f of xx again on this point, and this is again positive. Cool. So this is also a local minimum. Now this function has two local minimum at different points, and out of these two local minimum, one will be absolute minimum. Now this is the function x power 4 plus y power 4 minus 4 x times y plus 1. If you look at the graph of function, this is the function. Now you can notice that there are two minimum points. Everybody can, I mean, point out these minimum points, this one and this one. एक आपका point है -1 और 1, दूसरा 1 और, ठीक है? ओके, एंड z उन दोनों पर आपका आ रहा है कुछ कम वैल्यू, लेकिन सेम वैल्यू आ रही है, उसको बोथ आर लोकल मिनिमम. This is contour plot. I don't think you will need it, and level curves around this. आप ये इनको खुद से देख लें. Okay. And this is another example, example number 4, and this is a polynomial function. We have to find highest point on the graph. It means we have to find maximum point. We have to target, if there is maximum point, we have to find that one. Find and classify the critical points. So first of all, critical points, their first derivative, equate them to 0, and equating them to 0 will require us to solve these two equations, and solution of these two equations will yield the result x is equal to 0, and then if we plug in x is equal to 0 in another equation, we get y is equal to 0. So we get only one critical point, 0, 0. Now there are 3 more values of y, right? So in the end, we basically have all these values: 0, 0, 0, minus 2.54, 0, 0.64, 0, 1.89. Okay, so all these 4 values, these are the critical points. Just solve these two equations, then forcing both equations to 0, and then we get these 4 values. Now check, apply the second test on all these 4 values. First we need to find d. So this is, I mean, very nice analysis. So these are the points. Okay, sorry, I'm wrong. So these are not the points, but these are the points given in first column. These are the critical points. 1, 2, 3, 4, 5 critical points. And at this critical point, d is positive. At these critical points, d is positive. These two critical points, d is negative. It means these are saddle points. Now, if d is positive, f of xx is negative, it means this is local maximum, and D is positive, f of xs is negative, so it is also local maximum. Value of f is 0 at this point, and value of f is 8.50 at this point. So out of these two local points, this is the point which is absolute maxima, or the highest value. Okay, so 8.5 is the result. This was the function. We had quite a few, local two maximum points, this one and this one, and this was perhaps saddle point, and yeah. Okay, so example 4, and there is another example, number 5. Find the shortest distance. So this is, let's say, example in a somehow different test. So I am leaving this for the next session, so we will start from here in the next week. So let me mention it clearly. So okay, just to remind myself, so week 11 will start here, and till now I'm uploading this. Thank you. If you have any questions, anyone around for questions?
No, sir, questions now.
Okay, thank you. Recording will be available in a few minutes. You can watch, and if you have any question about exam,